Good morning and welcome to the fifth webinar of the Resilex webinar series. I'm Giulio Puggiaroni, Communication Dissemination Manager for the project Resilex, and I will be moderating this session. You probably have seen that in the past webinars, we have focused a lot on photovoltaics and also batteries. This time we focus on a different topic, which is one of those covered by the Resilex project, which is the recovery and valorization of mining waste, because Resilex has also a great focus about mining and mining waste from which we can recover valuable critical materials. So today I'm joined by Lidia Fernandez Rojo, project manager at Setaqua, one of the partners of Resilex, and also Tamara Martinez, R&D engineer at Tarsis Mining. So welcome Tamara and Lydia, and for our participants today, I remind you that we will share the slides after the end of the webinar. We will upload the slides and the recording on the Resilex website, and I will share the link in a while in the chat. If you have questions, please use the Q&A tab to post your questions. We will pick them up after the presentations are done. So enough from my side. I will give the floor to Lydia for presenting her part, her work done at Setaqua. Lydia, the floor is yours.
Okay. Thank you, Giulio, for the introduction. I will share my screen.
All good?
Yes, I'm looking for the presentation. Sorry, no, this is no. No.
In the meantime, I remind to our audience that all the previous episodes in the webinar series are already available, and as well the presentations. And also, if you browse on the website, you can download the fact sheets that focus on all the specific aspects of the project. Okay, I see the presentation, so Lydia, you can start.
Thank you, Giulio. Good morning, everyone. I'm Lidia Fernandez Rojo from Setaqua. As Giulio said, I'm project manager and researcher in with a background in environmental engineering. And today I will talk about the innovative circular treatment for recovering critical and valuable raw materials from acid mine drainage. First of all, I would like to present Setaqua. Setaqua, we are a research, development, and innovation center based on a unique public-private collaboration model. We belong to the big engineering company Veolia, and what we do is that we offer solutions in the water sector. We are mainly based in Spain and in Chile. We have 3 main offices in Spain. The headquarters are located in Barcelona, and in each one of these sites, there are a water utility, then a research center and university in the governing board of these offices. We also have offices in Andalusia, where we have, for example, here Hidralia, which is the water utility there. Also, as a research center, CSIC and the University of Malaga. And in Galicia, we have CSIC and in this case, the University of Santiago de Compostela. Then in Chile, we have Aguas Andinas and the Technical University of Federico Santa Maria. So here I will first explain the innovative circular treatment train. So this is the whole treatment train where we treat from one side acid wastewater and from the other side mine waste. But in my presentation, I will focus on the wastewater valorization route that is composed of 6 different units. Then I will go one unit per one, reviewing the main results of each one. And then Tarsis Mining will explain the main results on their 2 units for valorizing the mining waste. In our case, I would say that the focus was to treat from one side the acid mine drainage and also recover the valuable compounds in order to compensate the cost of treating these waters. The first treatment step was the physicochemical unit. And here the objective was to remove iron and aluminum. And we have a pilot that has this appearance. So here what we did is we treated the acid mine drainage from Tarsis. And by the addition of caustic soda, we remove iron and aluminum in the form of hydroxide or hydroxide sulfates. So this is a simplified formula. And the water we treat in that case, as you can see, is an acid, exhibits an acid pH, has a high sulfate content, in average 40 grams per liter, also high iron and aluminum content, so iron about 2 grams, aluminum about 0.4 that we remove in that step, and also had valuable compounds like zinc, copper, cobalt, and nickel that we will recover through the whole treatment train. So in this first step, what we did is that we wanted to optimize the iron aluminum removal while avoiding the co-precipitation of other metals like cobalt, nickel, copper, and zinc. So we did first pre-commissioning studies in the lab, and we determined the optimal pH for that, and it was 4.5. Also, we did test with the pilot before starting the treatment of the whole water, and we determined that the optimal residence time would be 2.2 hours. In the whole operation, what we achieved is an average of more than 99% and 85% iron aluminum removal at pH 4.5. However, we observed an undesired removal of copper in the sludge, a minimal removal of cobalt, nickel, and zinc, which was a good news since we wanted to them to remain in solution. Thus, you can see this result in the graph. So in orange, in dark orange, there is original water from Tarsis, and then the clarified effluent with light orange, and the removal for each of the cases. So for copper, for example, it can, in average, it reaches 50%. Then we also analyzed these sludge and with the scanning electron microscope, and we saw that the sludge were dominated by iron with sulfate and aluminum, and this is consistent with spaces like Shermanite or base aluminite that precipitate in this environment. Then the second step was the anaerobic membrane bioreactor, and here the objective was to generate sulfide for metal sulfide precipitation. So the simplified formula here is the one that is written here. So we add some carbon source. In that case, we add glycerine, and then we promote the sulfate reduction. And we obtain this sulfide that we will use after to precipitate metals. You can see here the pilot. It was a compact pilot with other units inside that I will explain later on. For the results, here we operated successfully the pilot for 260 days in 4 different phases, where we modified the chemical oxygen demand and sulfate ratios. The first phase consisted on the culture enrichment, where we work in batch with a synthetic inlet water. Then phase 2, we work in continuous mode with synthetic inlet water. Then for phase 3, we work in a circular treatment loop, which means that we were using as inlet for sulfate the, the same sulfates that are contained in the acidic mining waters from Tarsis. They are not synthetic anymore. And then in phase 4, we treat high sulfate synthetic inlet again, but with higher sulfate concentrations. So we achieve, in average, I would say 70% sulfate removal, but we reach up to 95% in phase 2. We measure maximum dissolved sulfite of 300 milligrams per liter in phase 3 and removal rates up to 4.7 grams per liter per day, with an average of 1.4 grams per liter per day for the whole operation. Then we also saw a good resilience to feed changes, which means from when we changed from phase 2 working with synthetic water to phase 3 that we were working with real water, we saw that the consortium adapted well. And then we also analyzed the gas composition, even if it was dominated by methane in the there were also some, of course, there were some sulfite in the gas. So here the point is that we probably would need to improve the sulfate reduction activity and decrease this methanogenic activity that we know that we cannot completely remove it, but we can try to allow it to avoid losing some of the, or to employ some of the carbon source to produce methane instead of this hydrogen sulfide. And then we also analyzed the bacterial composition with a 16S RNA metabarcoding. And we saw that the sulfate reduction bacteria were low in abundance. However, what we saw in the bioreactor is that they have significant sulfate reduction activity. And this is consistent with other studies because even if the genes are not numbers there, it does not mean that the genes that are there are expressing. So for that, we will need to do RNA, we will need to analyze the RNA activity of these sulfate reduction genes. Then in the anaerobic membrane bioreactor, so we have the bioreactor, which has a couplet membrane. In that case, it was a ultrafiltration membrane that is here. The bioreactor is behind this. And the objective was to remove the suspended solids that separate the organic matter to be reintroduced to the bioreactor. For the filtration, we operated in batch mode for 1 or 2 hours for a total of 31 filtration cycles, and we did not observe significant fouling for that operation time. And what you can see here in this picture is on the left, we have the appearance of the feed water. Then it works in batch, concentrating the concentrated stream. So at the end of each cycle, concentrate is darker. And then we have this permeate, which has a low turbidity. So concerning the permeate quality, that is what we evaluated. We saw a reduction in the volatile, solids, turbidity, and chemical oxygen demand from the feed to the concentrate. Sorry, from the feed to the permeate, I would say. And then we saw similar pH and electrical conductivity and the sulfate that was maintained between feed and permeate because it does not affect the membrane on these parameters. And what we saw is that the permeate that we obtained could be potentially be reused for irrigation after further treatment. For example, after removing excess sulfur. And also we need to remove some of or reduce the electrical conductivity of the permeate if you want to be used for irrigation. But here we have a key KPI in the project that was to reduce the acidic water discharge that was currently being done. Keep in mind that these waters are currently stored in open pits, so they are not treated for the moment. And if we compare what is having done now with that, we can say that with this treatment, we can reduce the 90% of acidic wastewater discharge compared to the current scenario, which is really good because we will only generate kind of 10% of waste. Then next step was the sulfide precipitation unit. So the objective here was to recover zinc and copper sulfides. As you can see in the picture, here we mix from one side the clarified effluent from the first physicochemical unit, which did not contain iron and aluminum anymore, or very small amounts of iron and aluminum, and we mix it with sulfide generated in the bioreactor. Here, what we did is we performed different tests at different hydraulic retention times, different pH and different sulfide concentrations. We know these reactions are fast; they are not kinetically controlled. But when we mean hydraulic retention time, we test it because the mixing it has an effect on the mixing of the two solutions in the reactor. So at the end, it has the hydraulic retention time and the mixing effectiveness has an effect on that. Here we have the plot. So on the plot above, we can see the results at the low hydraulic residence time. So we observe for the copper line in red that there is a high copper removal at all the dissolved sulfide concentrations. And for the rest of the metals, we see that zinc, cobalt, and nickel are removed medium to low proportion. So the nickel and cobalt removal, the low nickel and cobalt removal are is a good news because we wanted to separately or selectively recover it later. However, we wanted to improve the zinc removal here. Here we also show the aluminum. They do not form sulfides, but since this unit has an important alkalinity, aluminum is also removed in the form of hydroxide. So this is why we put it here, but they are not removed as sulfides. Then, if we look at the high residence time, we see that all the metals are easily removed from water, but even we lose cobalt and nickel, and we see that at the dose of 60 milligrams per liter, we also achieve near complete metal removal. So that's true that here we also test higher pH. So at the end, none of these conditions were the best ones since we wanted to retain copper, and we wanted to remove copper and zinc and retain cobalt and nickel. So here we remove a lot of almost complete. There was almost complete removal of all of them. So if we want to work further on that, probably we will need to work with a low hydraulic retention time, but probably putting higher sulfate dose and keeping the pH about 5. What we also analyzed the sludge from here, and on average, it contained about 20% of zinc and 6% of copper in the form of sulfides. So the outlet of this sulfide precipitation unit went to the ion exchange, where here the ion exchange resins preferentially retain cobalt and nickel. The objective was to recover them afterwards with sulfuric acid in a concentrated solution. Here you can have a look at the pilot we use for that. And here you can see the resins that we use. So each operation cycle is formed by 3 steps. First, there is the metal retention, where you treat the water and metals are retained onto resins. Then there is the pre-elution, where you remove hardness, for example, calcium and magnesium, and desired calcium and magnesium that are retained on these resins. And then you do the final elution with a concentrated acid to recover cobalt and nickel. Here you can see a results of 2 of the experiments. So in all of the cases, we retain more than 90%, 95% of cobalt and nickel. However, we did not reach the saturation in any of the cases. And what we observed that with the employed resins, we achieved 2.2 milligrams per cobalt and 0.9 milligrams per nickel per gram of resin. And we also see that there were the retention of other metals here that were zinc, iron, and copper that were not probably efficiently removed in the previous steps. So they were competing for the retention on these materials here. And then the next steps were the elution experiments, where we work with different pre-elution volumes, 6 to 12, one bed volume corresponding to 0.5 liter, and different acid sources. So we tried either commercial or acid from Tarsis mining. You can see here dilation efficiency and the recovery of cobalt and nickel. So what we observe is that once we work with longer pre-elution steps, it means with 12 bed volumes, it decreases impurities at the final elution solution that we obtained, because we remove calcium and magnesium before, but also increase cobalt and nickel losses. This is why the recovery of cobalt and nickel here is lower than in the experiment on the left, where we work only with 6 bed volume of the pre-elution. Here in these 2 experiments, we reach between 97 to 80% recovery of cobalt, and we concentrate cobalt about 20 to 87 times, and we obtain a final solution with 0.2 grams per liter of cobalt and almost 0.1 grams per liter of nickel in the alloy. Then we also test sulfuric acid from Tarsis mining. And in that case, the elution step was shortened because we have limited amount of acid, and probably this explains why the cobalt and nickel recovery here was much lower. However, we checked the Tarsis produced and it has a high quality and has all the requirements we asked for. Then next step is the acid recovery unit, which consists on a nanofiltration. So the elution employed in the ion exchange goes to this membrane, and here the objective is to concentrate cobalt and nickel in the concentrated stream from the nanofiltration and recover sulfuric acid in the permeate, because in this keep in mind that this exhibits an acid pH below 1, and under these conditions, sulfuric acid is in the form of disulfate, which means has 1 negative charge. So it is not rejected by the nanofiltration membrane, so it can permeate. And this is the way we can recover sulfuric acid in the permeate. And the membranes employed here are special for supporting acidic pH. Here we operated with synthetic solutions because the amount required for this pilot, as you can see, it was a kind of medium one, so it required 200 liters for working, and from the elution of the previous step that we recovered 3 liters instead of 200. So we work with synthetic solutions, and each run had a duration of 2.5 hours. And here you can have a look on the cobalt and nickel concentration factors and concentrations in the beginning, so in the feed and in the concentrate. And of course, in the permeate, we cannot see because all the cobalt and nickel went to the concentrate. So at the end, we increase the concentrations ninefold for cobalt and nickel. And sulfur, which is not here because it was out of range for this plot. So what we saw is the largely permeate as bisulfate, and we recover an sulfuric acid of a concentration about 0.9 molar that was able for reuse for other purposes. And then the last step of the wastewater valorization route consists on evaporator crystallizer. And the objective is to concentrate cobalt and nickel and recover the metals in the form of crystals. Here you can have a look on the setup. So first we work with either addition of caustic soda to first concentrate the metals as hydroxide, then resolve them with sulfuric acid, and then it went to the evaporative rotator, to a rotative evaporator, sorry. So as I explained, this step working in two operation cycle, the pretreatment, which consisted on hydroxide precipitation plus acid ready solution, and then the evaporation crystallization. And here you can show the result from this pretreatment step. So here we work with two different of streams as inlet stream. We either tested the ion exchange elation effluent directly, skipping the last step that I presented, the nanofiltration. And then we also test, of course, the acid recovery unit and the nanofiltration concentrate effluent. So we tested these two in order also to assess if the nanofiltration was necessary or not, or we could skip that step. What we saw here is that when using the ion exchange eluate, concentration factors for cobalt and nickel are about 3 to 5, but we lost about 3% of metal with this pretreatment. Here you can have a look at the concentration factor. And when we work with the nanofiltration, since this solution is already very concentrated, when we try to concentrate even further with the hydroxide precipitation, we did not. We did not reach to reduce the volume of the hydroxide sludge that is formed. So at the end, the concentration factor is lower than 1. It means we lose some of the valuable metals there. So if we are using this acid recovery unit, it makes no sense to employ this pretreatment. So you have to go directly to the evaporation crystallization step. And here we can show the results of the final sludge. So with the nanofiltration concentrate without pretreatment, here where you can see my arrow, we reach a higher cobalt and nickel recovery, and we obtain a crystal with about almost 80% of cobalt and almost 6% of nickel in the crystals that were in the form of cobalt and nickel sulfates, different hydrated sulfates. And then when we use the ion exchange solution effluent, what we saw is that cobalt and nickel concentration are much, much lower because they were not enough concentrated for these steps. So at the end, we did not obtain a valuable crystal for that. So from this, we thought that it is important to use the acid recovery unit. So to not skip that point because it is really helpful to concentrate the metals further. And then we also calculate the operational expenditures of all the different units. So here we calculate it with two different units as euro per cubic meter of acid manganese and euro per kilogram of valuable metals, considering valuable metals as copper, zinc, cobalt, and nickel. So what we see here is that some of the units has a high cost, like the anaerobic bioreactor, but there are some units that has a negative cost, which means that there are revenues for the selling of these valuable metals, which is really important in the evaporator crystallizer. Cobalt and nickel has a high value revenue, so it can help to compensate the cost of the rest of the units. So at the end, I mean, the mining company has to pay. It's not they do not the selling of the metals do not compensate enough for the rest of the operation expenditures, but at the end the price would be 3.35 euro per kilogram of valuable metals or 1.24 euro per cubic meter of acid mine drainage, and it is way better than the conventional treatment with lime addition that including the waste the managing of the waste, it could be around 4.12 euros per cubic meter. Thank you very much. That was my presentation, and now I will give the floor to Tamara to continue presentation.
Thank you, Lydia. In the meantime, I recall to the audience that you can post your questions in the Q&A tab and we will pick them up later. So Tamara, you can share your slides and then we move on to the second part.
Yes, thank you, Julia. Give me 1 second.
Okay, we see
nice. Okay. So, good morning, everyone. My name is Tamara Martinez, and I'm a R&D coordinator at Tarsis Mining. And for me, it's a pleasure to be here with you and to report on the progress made and the final results achieved. So, thanks, Tetako, for the progress. And before we begin, I'd like to briefly acknowledge the team behind this project. So, this has truly been a collaborative effort, and I'm really grateful for everyone's contribution. Okay. So Tarsis Mining is the only company of a 100% undiluted capital dedicated to the metal mining on the Iberian Pyrite Belt. That is one of the largest polymetallic sulfides reserves on the world, from Portugal to Seville, and it's located in Huelva and is part of the Mactel Group, a Spanish technology-based company with over 35 years of experience. Since November 2018, the company has carried out an intense evaluation of the mineral resources, carried out around 200 drill holes between 2020 and 20 years, and 20 and 22 accumulating more than 76,000 meter drill and analyzing more than 23,000 samples here in Norway. In 2023, Tarsis Mining began experimenting with different metallurgical routes to improve the recovery of copper, lead, and zinc, and gold and cobalt. So regarding on that, recent studies have confirmed the continuity of mineralization at depth, and significant mineral resources has been identified. So for the project, a total of 3,000 liters of water from Fila Norte was sent to the TACO for testing. And regarding to the experimental setup, this innovative treatment has been divided into 2 stages: furnace and combustion treatment and sulfuric acid production unit. So regarding to the first objective is the thermal oxidation of solid waste to produce sulfur dioxide, and Tarsis prepared an analysis sample from the extraction and the industrial sections For this stage, 50 kilograms of material waste were prepared and characterized in terms of dry weight, moisture content, density, and elemental composition. So the material was brushed in a yaw presser and reduced to a particle size of 2 millimeters. Moreover, was grinded in a ball mill, and after that, batches of 200 grams were taken and pulverized in a pulverizer mill for chemical characterization to a particle size of 75 micrometers. This is the furnace that you can see in this picture, and the combustion gases treatment installation with cooling, filtration, purification, and extraction gases stages. Related to the operational plan was focused on 3 lines: water cooling, hot gas to safety vent, and tempered gas to the acid plant circuits, in which several leg steps were carried out prior to commissioning. After that, Tarsis Mining tested the final assembly with low sulfur content in mining waste from Tarsis. So after that, continued the experimentation with high sulfur content around 40% weight by weight. So regarding to the commissioning phase, several tests have been carried out at different inclination and rotation speed in the furnace to present the experimental residence time data with a total feed rate of 1 kilogram per hour and a bulk density near to 4 tons per cubic meter. To determine the physical solid properties, in this first graphic representation, we can see the particle size curve obtained from a particle size analysis. This shows the particle size of the material, and we can see two situations, a dry and a wet grinding at different times between 5 and 45 minutes. And here you can see that the particle size obtained is directly proportional to the grinding time until the optimum time is reset. So in the second graphical representation, the particle size is obtained at 15, 20, and 25 minutes of grinding can be seen, both in dry and wet media. So it can be seen how a wet medium also favors the grinding process, obtaining smaller particle sizes at the same operating time. The furnace was operated under the selected optimal roasting condition during pilot scale validation, how you can see in this table. And this picture shows the appearance of the sulfur-rich solids before roasting and after roasting at 300 degrees and 750 degrees. So the final roasted solid exhibited an intense color tone that varied with the extent of the reaction within the particles. So regarding to the chemical properties, interesting results in the calcine has been achieved, and it's really important for us to continue and open it to another researching project. So the second stage is the sulfuric acid production unit, in which sulfur dioxide is synthesized from sulfur dioxide and dissolved in water through a contact process to obtain sulfuric acid. To meet Zetaqua's requirements, 3 acid production plants were installed here in Tarsis Main. So the optimization phase in Italy focused on fine-tuning the plant operating to achieve the highest acid purity using synthetic reagents. So during this stage, temperature profiles, flow rates, reagents ratios, and residence times were adjusted. The main objective was to identify the optimal operating condition that maximize the product quality while maintaining safe and stable operating. So an acid purity near to 82% weight by weight was achieved, optimizing the sulfur dioxide cooling and the sulfur dioxide combustion setups. So the integration tests were essential to demonstrate the stable operating of the combined furnace and acid plant configuration, and to assess it ability to produce acid from the roasting of gas. So during the experimental campaign, 11 independent sulfuric acid solutions were used for calculation and to evaluate process reproducibility. So the sulfur content here we can see in this table that the sulfur content decreases by more than 50% between the feed and the calcine, corresponding to a sulfur dioxide conversion efficiency near to 83% in the test number 10. This represents a significant conversion and a purity of 38%, particularly considering that the initial sulfur content of the feed was close to 40%. So the purity of the produced sulfuric acid was primarily governed by furnace temperature, which set the maximum attainable conversion. So at low intermediate temperatures between 100 and 450 degrees, incomplete oxidation was observed, and resulting in limited sulfur dioxide release and low sulfuric acid concentration. So in contrast, operation at 750 degrees maximizes the sulfur dioxide generation and stabilizes the acid production. Here you can see the different acid and base titration analysis. These cubes were obtained for two setups. Regarding to the sulfuric acid prepared from synthetic reagents and sulfuric acid produced from mining wastes. Finally, analysis of the final scrubber that you can see in this picture, which retains excess gases with 1 molar of sodium hydroxide and located at the final stage of the acid plant, showed that approximately 60% of the recovered sulfur was present as sodium sulfate, consistent with partial sulfur dioxide oxidation and sulfur dioxide acid during sulfur acid generation. So, after installing an additional scrubber tube containing 3 molar of sodium hydroxide in series, the sodium sulfate fraction decreases to 25% and the sulfuric acid purity increases to approximately 40% weight, which was the maximum sulfuric acid achieved concentration. So these results highlight the alkaline tail gas scrubbing states as a key optimization point and indicate that multi-stage scrubbing can improve overall sulfur recovery and support future scale-up. And finally, here in this table, you can see the OPEX that we have been calculated before. Here you can see that the OPEX is above of the market price in Europe. So regarding on that, we have checked the different chemical reagents costs and the different electrical energy costs. And this system is designed for experimental validation for sulfur recovery pathways, treatment and valorization of sulfur waste streams, control sulfur dioxide generation and capture, emission reduction strategies, and circular economy demonstration. We think that the OPEX reduction could be achieved through heat recovery from furnace combustion gases, an industrial scale oxygen supply, the energy efficient acid cooling alternatives, and the optimization of the air and oxygen feed control in another scale. So thank you very much. And before we close, and before the question that you have, I would like to sincerely thank all my colleagues for their effort, dedication, and commitment throughout this project. And thanks to your hard work and collaboration, we have been able to successfully bring this forward. So it has been a real pleasure to be part of this team. So thank you very much, everyone.
Thank you very much, Tamara.
Yeah.
So getting back to Lydia, I have a question perhaps. You mentioned the recovery of iron and aluminum that were achieved in your work. Uh, Question is, are these metals, they do require another treatment after the recovery you perform? And then moving more to the business case, so how can this work that you carried out inside the Resilex project can take the form of an actual business? I mean, you mentioned about selling the metals, the materials. But do you have, can you share some details like the potential customers, the potential applications of these recovered metals?
Yes, sure. The first question is, what are we doing with the iron aluminum that is removed in the first step? So normally this, as we consider it, these are treated as waste. This is what is done right now. I mean, when in the mining companies, when working with lime addition, they of course remove iron, aluminum, and other metals, and they treat everything as waste. So this part we consider it as waste. However, they could contain some valuable mineral phases like shermanite that could be, if refined, used, for example, as adsorbents for other metals in other operations, for example. And also another use that could be defined for this is the for filling the voids in some underground mining, for example. Considering that there are no, I mean, after doing some leaching tests and so on, the underground mines need also to fill, or underground mines, or also the tailing ponds, for example, needs to, once stabilizing them, there need to fill some of the voids inside, and this could be managed there. But what we have considered so far is to treat it as a waste. And for the second question of the business case, here the point is that the mining companies need to treat these waters if they want to restart the exploitation phases. So far there are many abandoned mines in Europe with stored waters, like is the case of Tarsi. So these mining companies need to treat this water if they want to start again their operation. And they need to treat it somehow. So at the end, they will they will spend some money on that. So at least what we propose is a treatment that can compensate the cost of treating these waters by recovering other valuable metals. For example, as I said, zinc and copper, which can be directly sold to these mining companies. They can be incorporated, for example, in the metallurgical activity, but of course this would be as intermediate compounds. They need to refine it more, refine it more if they want to pure product of, for example, a pure copper or zinc product. So, but as an intermediate product, it can be sold. And the same for cobalt and nickel. So the point is that for battery grade, for example, they ask for a very high quality and purity. That's not the case, but this can be sold again as an intermediate product. And if not, there are other possibilities for these metals, like zinc, for example, can be sold for coating or as a pigment, uh, and so on. But this is how we structure our business case.
Okay, clear. And then getting back to Tamara, since I mean, from Tamara, from what we heard from Lydia, you're going to be the mining companies like Tarsis are going to be like the end users of this application. So perhaps in this or Horizon Europe project, we always talk about the exploitation and how to translate the research on the ground to actual innovation and actual steps further. So how do you see in the future this exploitation of the results done in Resilex in your activity? Lydia mentioned the wastewaters that must be treated. We were lucky to visit your mine a few weeks ago and see the amount of water that needs to be treated. So can you tell us a bit more on this?
Yes, of course. So for us in the future, we would like to scale up the pilot plant that we have been working before, because the sulfuric acid is a critical input in mining, used primarily in hydrometallurgical processes for the leaching and separation of valuable metals like copper, uranium, zinc, and vanadium from ores. So enable the efficient processes of low-grade ores. It's also used in metal purification, the production of phosphoric acid, and the treatment of mining wastewater. So finally, the sulfuric acid is a chemical compound that enables the activation of electric batteries that require and facilitates the battery maintenance. So its primary function is to conduct energy within the battery, for example, regarding to the Resilex project.
Okay, and perhaps one last question would be, do you see this? I mean, we know that thanks to the pieces of legislation in Europe, like the Critical Raw Materials Act, but also the new push on mining activities due to the need to reduce the dependencies from the outside of Europe.
Yeah.
Do you see, especially in Spain, since Spain is really a mining country, do you see a huge movement, a huge push for restoring mines or reactivating activities, at least in the Spain case?
Yes. We have different mining companies here in Spain and the rest of Europe regarding that. That have a mining wastage and industrial products from different companies here in Spain and the rest of Europe that has a sulfur content about 32%. This is the percentage. This is the strategies for us to use the material here in the pilot plant and the scale up in the future.
Okay, thank you very much. We are approaching the end of our webinar. So thank you, Tamara, and thank you, Lydia, for your presentations. Thank you for the attendees for their participation. And I remind you that the recording will be uploaded on the Resilex website when you will have the chance to download also the presentations. Also, all the other materials, I can tell you that there are tons of materials that are available on the website that you can download for free and get to know the results and the work done in Resilex. So thank you very much again. Thank you, Tamara, and thank you, Lydia.
Yeah, thank you to you, Julia, and the rest of people that attended the meeting.
Thank you, and see you in the next webinar. Bye.
Okay, thank you. Bye-bye. Have a nice day. Bye.